All right, I hear in the background familiar music that I like. I like blues music, string harmonicas, and wild guitars, and everything else. All right, make me clap my hands, tap my toes, get happy, and peppy, and bursting with love. All right, ladies and gentlemen, I'll wait for the music to fade away and let's see what we can do. All right, ladies and gentlemen, the music is now gone, so I now beg your indulgence. Okay, Watchwell is my name and natural philosophy is my game. And of course, for those of you that have seen the show before, you always know that the emphasis is to learn something here, and that's why we have Albert here as our iconic symbol of learning, because we have the desire to learn. And of course, over here, then we have our confused monkey who is riding the planet, and that's kind of like what it is all about. So, what we will do is, throughout the program, we will have the P.O. box on the screen and the program times for you to watch. So, this show is being shot before Thanksgiving. It's actually 11/19/04. I always hate to date them, but sometimes you kind of have to say when they're on, because sometimes they get replayed. So, just in case it gets replayed, then you know that there may be some material that's pertinent to that particular time, and sometimes it may or may not apply to a future date, but nonetheless, it's close to Thanksgiving. So again, we will have the P.O. box on the screen as the show goes on, and we have any questions and comments, you can get them to me. Now, what we want to do today, it's right, so as you say, you want to set the course of where it is you want to go, like steering a big ship. What we want to do today is, the last time on the program, I was starting something a little bit different. I was starting kind of like not so much mathematics, solving algebra types and geometry types, but we were talking about the history of certain mathematicians. And I want to continue that for a little bit, and then the second part of the show is, there was someone who asked me about real specific algebra, algebra. And it has long been my hope from this show that there are, like, perhaps, some teachers in either high school level or junior high level, either math teachers or science teachers or physics teachers or chemistry teachers that would watch the show and then kind of use it as a springboard to say, well, now that's what so-and-so said, so maybe I can try that technique on you. So we will try to get some of that for you, and then if we have more time, we will have our kind of like our Where Are We segment with the Farmer's Almanac. But so we have a few things to talk about. So the show again is being shot before the 19th, so that's before the what they have the Thanksgiving Day, and we will get into that. I just have a couple quick comments. Now, of course, now that the election is over, we all know now that we have the George Bush regime for another 4 years. So it was Senator Kerry who was not able to bring a fin de regime de Bush in November 2nd. So now we have the Bush again. And of course, the Bill Clinton Library was opening up, and there were 4 presidents down there in the flesh seeing the thing open up. So it was a great day for Bill Clinton lovers. So we have the politicians. Now, what I want to talk about is, I'm going to kind of, again, this is something I just want to kind of follow through on. And like I said, I don't usually do these kind of lectures. This is almost more like a kind of like a college lecture series. So what I'm going to do for you here, what I did is I took, here you can get a kind of close-up, Andy, you can see, again, I have, there are no secrets in the Watchwell show. What I did is I took a certain mathematicians which I thought would be, kind of important and perhaps shine some light on history math, and I cut out little clips, from a couple books of knowledge, and I just put together a little collage, and I figured that this would be about the size of something that you could tackle in a half an hour's time. And then when I get through with that, then I really will do some real algebra. So, in 25 words or less, and probably in about 25 minutes or less, I'm going to try to give all of you a little bit of a treatise on mathematics, more specifically applying to geometry. And, of course, that is the key factor. See, the concept, again, we're going way back here. So what's about learning is getting the foundation. And the fact that I'm talking a little bit more about geometry than algebra is being done for a specific reason. And what it is that a lot of people don't get on base when they start studying algebra because they have a little problems with the kind of like the abstract and then understanding word problems, trying to decipher word problems, to put together, the various premises to solve the unknowns. And that gets difficult, and kind of like the beauty of geometry and, of course, descriptive geometry, which combines algebra and geometry, is that you, in addition to solving things, you also are kind of like making a picture or a diagram to go what it is that you're working on, and that helps. So that's specifically why I kind of picked the geometry aspect, and then that will segue into my algebra. But for this day here, again, I'm not kind of like a university type of lecturer, but I will just throw a few things at you, and I hope that you can get something out of it. Now, in terms of geometry, okay, in 25 words or less here, we meaning all people of the Western world, owe an unbelievable great debt of gratitude to the Greeks, right? It is to the Greeks that we owe very much. Much of the modern geometry and understanding, much of the astrology and everything was started with the Greeks for the most part, let's see, do I want to come back to Karl Gauss? I'll let Carl Friedrich Gauss go for a minute. Basically, about 400, I'm just going to do this a quick timeline here. About 400 BC is when there was a much geometry taking place in Greece, and of course there are many familiar names that come out of this area. Again, this is going to be pretty accelerated, and then, names such as Euclid and Euclid and Archimedes and Apollonius and Hippocrates, and all these people were famous Greeks, and Heron of Alexandria, and so on and so forth. So there are many Greeks. So just to kind of just make that big lump, is that much of the original geometry came, from Greece. And it's kind of interesting to note that all of this tremendous wealth of mathematics was formulated, over 1,000 years before Christopher Columbus sailed. But yet, for some reason, all of the culture of the Greeks got lost, and then the Romans came and gone, and then by that time, back in Northern Europe, they were thinking that the world ends, you're 10 miles out on the horizon. So it just shows that, one culture can be advanced and how it can get lost. Okay, so again, that's just a big blanket statement. So we owe much to the Greeks, and I don't want to go into too many others because I want to kind of make a big fast forward. So after the Greeks, like I said, there are many people that were doing this way before the time of Christ. But then if we we want to fast forward. Also, having said that, the Greeks laid the foundation of much geometry and astronomy in a very kind of a comprehensive way. But now what we want to do is we want to fast forward to get into the concept of what's called descriptive geometry, and what we are familiar with. And basically, what we are used to seeing is, kind of like the concept of, some graph, whether it's, that kind of a graph, or whether it's a straight line graph, this concept of this relationship between x and y as some kind of a function. And again, it's like I said before, something that you can sink your teeth into, is that if you can combine a picture or a chart or a graph with what it is you're trying to solve, it makes it all more easy to visualize. So I want to spend just a few short minutes with a Frenchman, René Descartes, who lived from 1596 to 1650. And again, I'm going to kind of jump around here because, again, in a kind of a half-hour format, in a kind of an open show, you just kind of go where your emotions take you. But we'll talk quickly, just a few short minutes, about the René Descartes, who lived again from 1596 to 1650. And again, we are talking about the Descartes, René Tartes. And what René Descartes was most credited for, he was actually a philosopher and a mathematician, but what René Descartes is most credited for, and I'll read a little excerpt here, just a short paragraph, is most credited with is developing the concept of what they call the Cartesian coordinates, and he's basically the father of what they call analytic geometry, where you develop the actual coordinate system, where you can make a mathematical correspondence between an x point and a y point, and specifically say kind of like what it is specifically. And here's an example. I don't know if you can get a close up of this, Andy, but here, this is kind of a concept of just a kind of a rough sketches of coordinates, and then this is just a sketch I used in just geometry, where you're actually showing, the real mathematical points, and that's the whole concept. But let me read a little bit about this Frenchman who did this, and it's kind of interesting. So here, it springboards out a little bit. This is kind of goes past kind of like what you would hear in perhaps ninth grade algebra. This is from a book of knowledge, so this is maybe a little bit more highbrow into what you might hear if you were in a college lecture. So I will, what can I say? I will say that it is my expectation that my audience is so sophisticated that they can drink all this in. So I will give to you a couple paragraphs about René Descartes. Okay, so René Descartes lived from 1596 to 1650, a French mathematician and philosopher, educated at the Jesuit College of Les Fliches and studied in Paris. After serving as a soldier, he settled in 1629 in Holland, where he published most of his work. He invented the method of combining algebra and geometry, and that's specifically what I was just saying, now called analytic geometry, in order to correct his faults with the virtue of each other, to correct the faults with the virtues of each other. That was his quote. That's what he was saying. In other words, he was always proving that things were wrong, and that's how he defined them to finally be correct. Okay, so I will read on quickly. René called the Cartesian, what he called the Cartesian marks, the turning point of history of philosophy. And again, it's what I was saying is that he developed the concept of making pictures and graphs and charts to go along with abstract thoughts. And up until that point, people were studying geometry, but then there was some math with it, but they were not connected. And of course, that was his kind of like his big thing, is that he wanted to do this. Okay, Descartes is also considered the founder of modern epistemology, which is the meanings of words, and his metaphysical distinctions influenced all subsequent philosophy. Okay, but I'm going to keep on going. I'm going to read quickly. Dissatisfied with the persistent disagreement he found among philosophers, he set out to establish a new method of philosophy modeled on mathematics. He began in his Discours de la Méthode, which is, of course, translated to Discourse of Method in 1637, by doubting everything. And doubting is how he ultimately turned it around by saying, well, if I doubt, I have to have a body to doubt in. And that's where this concept, where you hear this famous thing you always hear in college, I think, therefore I am. So it really came about of his doubting. So he said, well, how, even if I'm doubting, I'm still thinking. So therefore I am. And so that famous college quote you hear is, I think, therefore I am. Of course, from the French it is, je pense, donc je suis, which means I think, therefore I am. So I am this person. So René Descartes was responsible for much of this. He also published a book, In the Principle of Philosophy. He proposed a cosmology embodying the theory of vortices to account for planetary motion, on and on and on and on and on. So René was a very more of a colorful picture, because he was involved in much philosophy as well as this. Okay, so I dwelled a little bit on René, but that will lead back into my algebra business. Okay, thank you, Mr. Descartes. So remember that one. So every time you hear that thing, if you were like in a college course and you say, I think, therefore I am, well, you can really score some points, and you can say, je pense, donc je suis. Okay, boy, your professor would be so impressed. Okay, I'm going to jump ahead. Again, there are many other, more colorful pictures. And again, the reason why I'm doing this is because a lot of times people poo-poo, people who study math and science, and they say, oh, they're just a bunch of boring borks. And so we're just trying to show them that we can spark things up as well. And a couple other people who are worth mention is there's any number of people. We talked about Carl Friedrich Gauss next week. There was also a famous Russian mathematician named Nikolai Lobachevsky, and there was also Johann Bolyai and Bernard Riemann. And these people, the timeline on these other people that I just mentioned was a kind of another, what would you call it, a kind of a mathematical renaissance, was around from about, in general terms, from about 1667 to about 1866. And again, and then this was a kind of like another colorful picture where there were a group of mathematicians. Specifically, if you look up these names, one would be Johann Bolyai, Lobachevsky, like I meant before, and Girolamo Sescari. They went back to much of the kind of the Euclidean geometry, and they developed quite a few parts of analytic geometry that I use today. Like if you study calculus, the name Riemann or Riemann sums would be familiar. If you study linear systems in Gauss, you will say, oh, the Gaussian method of that all goes back. So again, we're just saying that there is all a rich philosophical history that goes with mathematicians, more so than just the boring algebra that you hate while you're in school. So again, I just was kind of throwing a little bit of that out there for you. I don't want to get into all of this because in a half-hour show, you really cannot do that crazy much. I'll tell you what I'm going to do. I'm going to do, let's see, I'm watching my time here. I'm going to do somebody asked me to do some algebra problems, and I'll do a few. But let me do, I kind of missed it on the last show. Let me do just a real quick Where Are We segment, and then we will finish up the show, and I'll try to do just a couple little simple algebra problems just from my old algebra days. But it hasn't changed. Algebra doesn't change. But let me do just a real quick Where Are We, because we can do in this time. Okay, now we said before that we are shooting this show in November, and we're getting close to Thanksgiving. So what that means now is, of course, we know that the next, using the node system here, this was fall, and Christmas is now going to come up fast, and that's going to be at 12:21. So we are on the proverbial racetrack. So we got 9:21. 10:21, 11:21, so it's just before 11:21. So now our little earthy poo is now down this way here. And I have this little program at home where I can kind of put, like, in terms of degrees, where the Earth is, because it's based on the premise that it's basically 360 degrees is one circle around the sun, and there are 365 days in a year. So for the most part, you can ballpark it. You can say, well, then the Earth, moves like a degree a day, 1 degree a day, and then it adds up to 360. So it keeps on moving. So here we are on the racetrack. So we're like down here, like I say, 10:21, 9:21, 10:21, 11:21, 12:21. So we're like about this way over here. And we are approximately, if you would take this kind of like in trigonometry, you could say that our angle this way, with respect to kind of like the sun would be like 60 degrees, where it'll be like, say, 90 degrees when we're at that point. And of course, today it says on the calendar that today is the first quarter. And of course, and what that means is that the Earth is over here, and that the moon on this very day is in fact in line with the planet, where the moon is on the exact line of the orbital path. And that's why when you look up in the sky, well, you won't see it because it's raining, but if you did, at exactly 6 o'clock or 1800 hours, the moon is exactly 1/2 of a piece of pie. And that just means that the moon is exactly on the orbital path with the Earth. So that's that. And of course, and then the stars are here, there, and everywhere. But we'll get into that. I repeat this so much. And of course, the reason why I babble this stuff over and over and over is just to get people stimulated, that they will the hardcore people will look up and try to understand the informazione that appears in the Farmer's Almanac, and look up some other things about mathematics. I hope somebody will go and look up something on Descartes, or look up something, on Riemann or something, to get something out of it. Okay, so it looks like I got about 8 minutes here. So I'm going to try to do a couple algebra problems, real quickies. Again, just simple algebra, but again, the idea. Now, what I brought in here, excuse me, I'm momentarily off camera. What I brought in for Hugh today's, again, Watchwell is really digging deep here, Andy. Here I am. Old Watchwell is over 60 years old, and here he digs back, and he still culls information going all the way back to the days of high school. These were These were the kind of books that they made when dinosaurs roamed the earth. These books were published fighting off Tyrannosaurus rexes that were trying to eat the paper as the books were being printed. Oh, not really, but they're old books, but nonetheless, the principles, they don't wear out. So I just dug up a few old algebra problems from years past, and so I figured I would just kind of just spit out what I can spit out in a short period of time. And of course, they're the kind of problems like, like the dreaded age problems, right? The one, John is 10 years older than his father, and 4 years his father will be 1/3 his age, and all that stuff, the ones that you absolutely dread, to death. So I just picked a couple that I think I may have even used on this show before. But I'm going to do a couple simpler ones, and see if I can get one or two out of my body before the show ends here today. Now here's a real simple one. Now this is actually pretty good. Now this is something that you should be able to solve. Let's see if I can do two of them here real quick. Here's a real simple one, okay? And this is algebra, what they call, you solve these by substitution. When you have two unknowns, you have to somehow eliminate one of the unknowns and then solve the one unknown, and then after you get it, substitute back in. And this is very common. And now this is the kind of problem that probably somebody in 9th grade algebra should be able to solve, or probably a B-level student. Here's a real simple one. It says, find two numbers if their sum is 33 and their difference is 9. Okay, so I'll say it again. Find the sum of two numbers. Find the two numbers if their sum is 33 and their difference is 9. So what you got to do is you got to write down what you know to find out what you don't know. And I'm going to try to solve two quick ones here if I can. So here it is. Okay, so what I'm saying is, okay, A plus B, and of course algebra is always nothing more than representing numbers for something that you don't know. If I would say that A equals 10, well, then there would be no problem to solve, okay? So you're always saying that the numbers equal something. So we're saying that A plus B equals 33, okay? And then we're also saying that A minus B equals 9, okay? What it's saying is that one number is larger than the other. So here's what you got to do. Here's what I call, you got to do the substitution. So you take that and you say, well, okay, if you're saying that A minus B is equal to 9, then you also can solve for A, and then you say, therefore, or then, A is equal to 9 plus B. Okay, just substitution. This is all very logical. And then you just go through the process, and you say, well, okay, we said A plus B equals 33, so then you say 9 plus B, that's this B, equals 33. Okay, are you following me? A plus B equals 33. You solve this out. So then now you don't have an A and a B, but you only have a B and a B. Okay? Then you just combine them down, and then you say 2, because there's two B's, you say 2 B's is equal to 33 minus 9. Okay? And then, if you want to get rid of this B by solving it over here, you bring this down over here, and you get rid of this 2 over here, then you're saying that B is equal to 33 minus 9 divided by 2. And you grind that out, and the number ends up being 12. Okay, so B equals 12. Okay, and then once you have one number, then you can find the other number. So then if you say, well, if B is equal to 12, then you say 33 minus 12 equals 21. So therefore 21 is equal to A. Okay, so you have solved your two things. And then what you do is you go backwards and you check, see? And you can do this on a half a piece of paper. It's not really that hard. It's just setting it up. So then you check your numbers. So then you say, okay, 21, I'm going to check. You say 21 plus 9, I'm sorry, 21. Try it again. 21 plus 12 equals 33. And indeed it does. And then if you say 21 minus 12 equals 9. So you have solved your problem on both fronts. Again, this is just a type of problem here. And I'm going to try to spit out here one more real quick one here. I got about 2 minutes. And another one was, as you know, on the Watchwell show, I always talk about the Indianapolis race many times. Let's see if I can squirt this out. Okay, and here's another one. It says, this is out of a book that was published back in the 50s. And it says, the Indianapolis Speedway is 2.5 miles around. How long will it take for a driver going 106.25 miles an hour to gain a lap on a driver going 100 miles an hour? And, I'm not sure if I'll get this one out. Well, we'll see if we can squirt it out. Okay, I'm just trying to fulfill my promise. So on this one here, this is if I don't finish this, we'll finish this on the next show. This is the one where you used my familiar formula that the distance S is equal to VT, okay? And in this case, S is equal to the 2.5 miles of the track. And then this is a case where you have to quickly do what you call the velocity of B relative to velocity of A. Therefore, it's velocity of A minus velocity of B. And that means that you take that 106.25 minus 100, and then that gives you that small number of 6.25 miles an hour. I'm kind of just waiting for my music. 6.25 miles an hour as the speed that you put over here, and then you know the distance is 2.5 miles, and then you plug those two in, and then you get a time, and then I came up with, if you plug in all the numbers, it's like 0.4 hours, and then you multiply that times 60, it ends up being basically 24 minutes in theory. And then, of course, then that makes sense. So then if you have that kind of the concept of, one car is going faster, one car is a little slower, and it keeps on going and going and going. And then in theory, if both cars would keep traveling, and if they wouldn't pit, then one would pass the other car in 24 minutes. Okay, I didn't hear my music, but I think it is going on by now. Watchwell is my name. Natural philosophy is my game. And until we see you next time, bye-bye, and everybody have a wonderful Thanksgiving. See you later, alligator.